a lot of the things that are going to be said in the actual course. So rather than actually starting the topic, I thought I'd just say some sort of philosophical comments about the philosophy of motives and how that relates to Grothendieck-Teichmüller theory. So this is very much the unipotent side of the story. It's very different from the profinite situation, but it also goes way beyond the moduli spaces of curves and the pro-unipotent Grothendieck-Teichmüller picture. So it will appear very sort of different from what we've seen before. And at the end, I'll try and tie the ends together so we see what's going on. So the title is Periods. And a very influential paper, which I strongly recommend to everybody, is by Kontsevich and Zagier. And it's called Periods. And it's in a volume which has a very futuristic sounding title, Mathematics Unlimited, 2001 and Beyond. And it was published in 2001. But I strongly recommend this paper. It's really inspiring, and it's got beautiful examples in it. If you've just got 10 minutes, you can look it up on Google and read the introduction, and it's really, it makes you want to be a number theorist. I'll start off really copying from their paper, and they begin by recording the history of mathematics in some sense. We start off with the natural numbers. So please don't ask me if 0 is a natural number or not. I have no idea after living in France for such a long time. Then we have the integers. And very quickly, when you want to divide things, you realize you need the rational numbers. Then you want to solve algebraic equations, so you're forced to pass to the algebraic numbers. And then when you want to go a little bit further, calculate some integrals, you find that the quantities are non-algebraic in general, numbers like pi and so forth. And normally we sort of jump straight to the complex numbers, or the real numbers, which are pretty terrifying. And the purpose of this paper is to suggest that, in fact, a lot of numbers that are very interesting and important in mathematics sit in an intermediary class called P, and so P is the ring of periods.
Blackboard P with justice.
That's blackboard P. Since I have a blackboard, I can do this. Yeah, P, the ring of periods, and it's going to be a countable set. Okay, so their whole argument is that this class of numbers are somehow much more interesting than just the whole of R. The numbers that occur the most often in practice are very often in this class, or a closely related class. So again, from that paper, so that if you look it up, it will coincide. There's the first sort of informal definition. So there are many possible definitions which are equivalent, but the simplest is the following. So a period is a complex number whose real and imaginary parts, again, that's not so important, are integrals of, what do they say, rational functions with rational coefficients over something algebraic, so over domains in Rn, let's say, defined by polynomial inequalities. So something that's entirely defined algebraically. So it's not important, but one should take these polynomials also to have Q coefficients for the sake of argument. Okay. So here's some examples, again taken from their paper. So the square root of 2 is indeed the integral of dx over the domain 2x squared less than or equal to 1. So that's certainly a period. And in a similar way, it's very easy to show that all algebraic numbers are periods. That's a good exercise. The next example is pi. So what's an example of a number that's not a period? So there's no particular, you can construct them, of course. This is a countable set, so they're standard arguments, Gödel type arguments to construct them. But there's no example of a nice number that's known to be not a period. But it's conjectured, for example, that e, so e, of course, is exponential of 1. It's expected that this is not a period. But no one can prove this. Another example that's more relevant to the theme of the conference, zeta 3. So here's just one representation for zeta 3. To prove it, of course, you just do span this as a geometric series. And you get precisely the definition of zeta 3. So in the same vein, all the values of the Riemann zeta function are periods. All multiple zeta values. So I believe that, so Herbert wrote down an integral representation for the multiple zeta values a couple of days ago. That shows that they're periods. And so there are many other examples in mathematics. And I can't even begin to cover the topic in the depth in this paper. The whole theory of special values of L functions, periods of modular forms, all sorts of things fit into this box. But there's one class of numbers that are very important that I care a lot about in physics, not in mathematics, which they don't mention at all. And these are Feynman integrals in perturbative quantum field theory. And so, yes.
About your definition. Since you work in domains given by polynomial inequalities, it seems to be natural to consider functions whose graphs are also given by polynomial inequalities, semi-algebraic functions. Why it doesn't work? Why the definition is considered just only rational?
So that you can always rational is, so you can replace this with q bar. It doesn't change anything. So you can always since every algebraic number can be written as an integral of something rational. That's an exercise. Then you can simply add more integrals, and every time you see an algebraic number, you can replace it with more integrals to get that number. So you can always reduce to q. So this definition is slightly artificial. It's the most narrow possible, most specific possible definition. It's not necessarily the best way to think about it. Yeah.
But just two words, rational. Also, if you replace rational functions by algebraic functions, will it change?
No, nothing. So it's the same thing again. Mm-hmm. So this is the informal definition. The correct definition is where you take more generally any smooth scheme of finite type over spec q, and you compute some integrals relative to some cycles over this. So that will be the definition I'll give a bit later. So I thought you were asking about whether there's a good class of functions that underlie this thing, and that's a good question.
So if I take just
an
algebraic function, it's too big, just semi-algebraic. I mean, the graphs of these functions are also semi-algebraic variety.
Yes.
Will be enough. Is it still a period?
Yes. Yes, absolutely. Yes. I thought you were asking a different question.
No,
but that's what I see. Yeah. So these things are the integrals in physics are very interesting. If you open any research monographs or papers in high energy physics, it's just absolutely packed full of multiple zeta values and periods in general. So the predictions for the LHC come from theoretical computations, which are always periods. And that was one of the main motivating forces for studying multiple zeta values historically, the fact that they kept coming up in physics computations. So what's the general philosophy? General philosophy. So let's go back to the algebraic numbers. You have q bar over q, and we know from our earliest memories that the way to study algebraic numbers is through Galois theory, and particularly the absolute Galois group in this case, which is a profinite group. And the philosophy is that there should exist an analogous Galois theory for periods. So what does that mean? We should have, let's take P over Q, for example, and, well, make Q bar maybe. And there should be some sort of group here, and G will be a pro-algebraic group, not a profinite group, that somehow moves all these periods around and preserves all the structures, the algebraic structures between them. And so this is not a limit of finite groups, but a limit of algebraic groups, matrix groups. And so this thing is called a motivic Galois group. Okay, so the question then that I'd like to sort of give some ideas how to start tackling this is how can we compute the action of such a motivic Galois group on some class of periods. What's motivic about it? I'll ask me that question towards the end, so it'll come in naturally. As yeah, it's very very motivic. But this question, of course, is completely meaningless at this stage. Because we can't just sort of move numbers around. Because if you could, that would immediately imply very strong transcendence results for periods. If you think about it a little bit, the existence of a Galois group for Q bar proves irrationality type things for algebraic numbers. And these are completely unavailable for most periods. So the transcendence and irrationality questions are extremely hard. So Herbert mentioned that zeta 5 is not known to be irrational, so we don't know if it actually should be fixed by the Galois group or not. So this entire approach is scuppered, but you can get around this and replace numbers, replace this sort of naive picture where we just work with numbers with something a bit more algebraic. And that's where the motives come in. Okay, so I'll try and go very slowly, and I hope a lot of these concepts are very familiar to you. So cohomology. So I'm going to take X, a smooth scheme of finite type over Q. So don't really have to take Q, we can take something else, but for the purpose of this talk, I'll restrict to Q. And so think of some smooth variety. Then we have the Betti cohomology, which really, I should say, comes from some embedding of Q into C. In this case, there's only one, so there's no choice to be made. In general, you'd have to, if you had a number field, say, you'd have to choose some embedding. There'd be many possible choices. Then X of C will be some smooth manifold. And we can look at its ordinary singular, its complex of singular chains or cochains, and take the cohomology. So we have H Betti of the complex points. I'll take coefficients in Q. So it's actually defined over the integers, but I prefer to tensor with Q to have Q coefficients. So this is singular cohomology. But frequently I'll mainly consider homology. And I won't put the B in this case. And the coefficients Q will always be implicit. So we have singular homology as well. Okay. So that, I hope, is very familiar. Then we have de Rham cohomology, which is perhaps not so familiar. I should say algebraic de Rham cohomology. So this was defined by Grothendieck. So I'll write it H I de Rham X, and again with coefficients in Q. In general, the coefficients should coincide with the field of definition. So this is called algebraic de Rham cohomology. And the point is, in classical de Rham cohomology, you take complexes of smooth forms. Here we only take algebraic forms. Everything is constructed algebraically. So to simplify a little bit, in the case when X is affine, then it's something very concrete. H I de Rham of X Q is simply the cohomology of the complex of the global regular differential forms on X. Yes. Yes. Regular forms on X. So it's not at all obvious or trivial to see that this actually calculates the usual de Rham cohomology. That's the whole strength of Grothendieck's theorem. In the case when X is not affine, you have to take an affine covering and take hypercohomology. But in fact, for periods, we don't actually very often need to do that. So I'll just write that as comment. In general, we take hypercohomology. Okay, so let me give a very, very simple example. So let me just take P1 minus 0 infinity. Actually, I'll call this GM just to save. Save on writing it out every time. So okay, what is omega naught? Well, it's just Q Z1 over Z. This is, of course, this is spec. And omega 1 is the same thing with a dz. So this complex is just exactly this thing, dz. So this is the ring of global regular one forms, the module, rather. And the differential is the usual differential. So it's very easy to check that the H0, the forms which have trivial differential are precisely the constants. So H0 Durham is just Q, it's the kernel of this map. And the H1 are the elements here which do not have primitives. So H1 is just spanned by class of dz over z. Okay, and Betty. So for Betty, we take the complex points. So used to writing 0, 1, infinity. Of C is just C star, and that's homotopy equivalent to a circle. And so, as we all know, H0. So I'll from now on I'll tend to write homology in the Betty setting, just because it's what we need for the periods. And H1 is something called gamma naught, where gamma naught, for example, is some little loop around 0. Gamma naught. Okay, so then we have the Durham theorem. So really it should be the Grothendieck-Durham theorem, because the original Durham theorem relates to classical Durham cohomology. And it says that we have an isomorphism, which is often called a comparison from Betty to Durham. Hi Betty x Q. So you have to extend scalars to the complex numbers. Isomorph H. So that's an isomorphism. And it's a highly transcendental, as we'll show just in this simple example. So first I say, of course, this is given by integration. So to compute it, it's given by the integration pairing. C. So what we do is we take some homology class in Betty, and some differential form or some cohomology class in Durham, and you integrate the differential form over the cycle. And that's precisely what was classically called a period. So of course the relationship between these, of course, because the Betty cohomology is dual to the Betty homology. Okay, and so in this particular case, of course, what is the period? It's just the integral of dz over z around gamma naught, and that's 2I pi. Okay, so the periods I defined at the beginning of the lecture do not fit into this picture. they're slightly more general. So strictly speaking, I mean, one could call this really a pure, well, yeah, maybe I won't say that. To actually capture the periods such as the zeta values and so forth, this is not enough, and we actually need to consider relative cohomology. And this is where it starts to get interesting. So let me remind you of how this works. So when you do singular homology, you consider a pair of spaces, say Z contained in X. So for now they could be topological spaces. And we have the C dot of something, X or Z, is the singular chain, or chain complex of singular chains. And there's an exact sequence of complexes and so using this, you define the relative homology. So the homology of X relative to Z. So of course, I'm always going to work with Q coefficients. So the relative homology of X relative to Z is just the homology of this quotient complex. And so what is an element in relative homology? Well, it's represented by, every class is represented by some singular chain in Cx whose boundary, such that its boundary is in, so let's say Cn is in Cn minus 1 of Z. So it's something with a non-trivial boundary that's contained in the smaller space. And of course, so in this context, you have the long exact sequence of homology HNZ, HNX, HNZ relative, X relative to Z, HN minus 1, and so on. Okay, so I hope that's all extremely familiar. Okay, so then you have the same story on the de Rham side. And we can do a relative algebraic de Rham cohomology in the same way. So I'll go slightly a bit faster this time. So in de Rham, it's the same story. So now let's take, we have Z contained in X, both smooth and affine, to simplify. Though in practice we often need to take Z singular. So that's a slightly more complicated story. And then you can look at, for example, the mapping cone. Sorry, X to Z. And to cut a long story short, you can just define the relative de Rham cohomology to be the cohomology of the mapping cone, or better, the cohomology of the total complex of this bicomplex, for example. So what does a relative de Rham thing look like? You could think of it as a pair of differential forms. And the differential will be something like d omega x I lower star omega x minus d omega z. So I hope my signs are correct. I didn't actually check this morning. Maybe there's a... So at this point there's a kind of crucial remark which is a bit confusing if you've never seen it before. That if the dimension of x is equal to n, and the dimension of z is equal to n minus 1, then the funny thing is that an n form, well, z has no n forms. So any n form on x restricted to z vanishes. And so what you get is that any n form on x actually defines a relative cohomology class which in this notation I could write as omega comma naught. And its differential is obviously 0. Oh, sorry, yeah, thank you. Upper star, of course. Yeah, thank you. Of course. So any n form, if I take a d of an n form, I get an n plus 1 form, and that vanishes because x is the dimension n. And likewise, for the same reason, it's a closed form. So you actually get from an ordinary differential form, you actually get a relative differential form for free. And typically in the subject, people always just write, you typically only ever consider forms of this type, but we think of them as relative, as classes in relative cohomology. Okay, so now, and then of course we have the de Rham, a version of the de Rham isomorphism. So now you need to integrate pairs of forms against pairs of cycles. It's relatively easy to do that with Stokes' theorem. And what we get is, so formally from the previous de Rham theorem, an isomorphism between relative cohomology groups. So this seems like just some formal addition to what I did earlier, but actually it changes everything because we get a lot more numbers coming out as periods in this setup. This is really crucial. So now let me do an example. So it's the simplest possible example of a mixed motive. So it's typically called Kummer motive. And so we take some alpha in Q star, and I want to consider the pair of points 1 comma alpha sitting inside GM. So let's say P1 and so now let's compute the Betti homology first of all. So by the long exact sequence I gave earlier, we have naught H1 so I apologize for doing these calculations, but I was told to be very introductory and go slowly. That's okay. Then H1 relative, and then H naught of the pair of points, H naught of. So again, strictly speaking, I should take complex points everywhere, but I forgot to do that. So please, in your notes, put complex points everywhere, because when we're doing Betti, it doesn't make sense to just do it on the level of schemes. We have to take the actual topological spaces. So I'll put one in here, and please add the other ones. So this one we already calculated. This is Q. This we want to work out. This is just has two connected components, so it's Q, two copies of Q, and this is connected, so it's one copy of Q. So you can split off this, the last arrow, and replace it with a short exact sequence. Replace it with a short exact sequence. So we have this thing which we computed earlier. This was Q, and it was spanned by this little loop around 0. And then we have what we want to compute. So let me give that a name. So let me call this, by definition, M alpha Betty. Yeah. So the cumulative is going to be M alpha. Okay, so this is a slight abuse because I'm thinking about homology, so I'll put the B upstairs to indicate homology. So it's kind of non-standard notation, right? Yeah, so I should really say that normally when you do the Betty realization, one works with cohomology, and it's not very good to switch homology and cohomology. But for the purpose of this talk, I'm going to call this the Betty realization in homology, and in a minute I'll go back to the standard notation. So I'll just warn you now in case that's a bit confusing. So here then we just have Q coming from that. So the upshot is that M alpha Betty is just a two-dimensional vector space over Q, and we can write down a basis for it non-canonically. So we have 0, 1, and alpha over here somewhere, let's say. So we had this gamma naught from the absolute case, got nothing to do with the pair 1 and alpha. And then I want so one basis one generator is the homology class of gamma naught, coming from the absolute homology. And then there's something relative, so we need something with a boundary. And for that I have to choose a path, gamma 1, from 1 to alpha. So that's some choice of basis for MB alpha. And the key point here, of course, there is no canonical way to choose a path from 1 to alpha. I could wind many times around 0. There's no way to know how to get from 1 to alpha without some kind of choice. The Dram setting is different. So the Dram, so we do the same exact sequences. I'm just going to cut straight to the answer. In the end, we get a short exact sequence like this. We get a Q coming in. We get this time H1 Dram P1 minus 0 infinity relative to 1 alpha. So I'm going to call this M alpha Dram version. And then we have H1 Dram P1. So we already computed this thing. This was Q dz over z. And as I mentioned earlier, you can actually view this thing, you can pull it back uniquely and view it as a relative cohomology class. So this thing actually splits in the Dram setting. So what we have is, so M Durham alpha is a two-dimensional Q vector space again, as it should. And now as a basis, I can take a class of dz over z. And what am I going to take here? Well, strictly speaking, in this definition, I should take something that, if you look at what the mapping cone means, I should take something like a function on the points 1 and alpha. But by this remark I mentioned earlier, which here, you can construct lots of forms just by considering sort of absolute forms on the full space. So it turns out you can check, it's not a very difficult calculation, that the form dz will do the job. So I can view dz as a relative differential form. It has a non-zero cohomology class. As an absolute differential form, it of course would be exact because it's d of z. But you can check that this is a non-trivial cohomology class, and this thing does give a basis of M Durham alpha. dz you can take on the points 1 and alpha, and then with it, that defines a relative differential form. So if the function is f, it's 0, f, and you can check that it can be represented by dz, 0 if you calculate with the relative forms. Okay. So then, what is the period matrix? Period matrix means that you take your chosen base of Betti and Durham and you integrate them all against each other. So I integrate along gamma naught dz over z, gamma 1 dz over z, gamma naught dz, gamma 1 dz. And what you get, so the integral of dz over z around a small loop is 2I pi. The integral of dz over z from 1 to alpha is exactly the logarithm of alpha. And dz over gamma naught gives us 0. And integral of dz along gamma 1 gives us some rational number that we don't really care about, alpha minus 1. So normally it's customary actually to renormalize this basis so that you get 1 here. So perhaps I'll do that. I'll just put 1 here and rescale.
dz over alpha minus 1.
Yeah, alpha minus 1. Alpha minus 1, yeah, that's the correct sign. So that's the period matrix as you usually see it. Okay, and so the period matrix, of course, is given by a way to. So what we had was M Durham tensored with C was isomorphic to M Betti tensor C, and we're computing this comparison by choosing a basis over Q here, choosing a basis over Q here, and comparing them and seeing where they go to. And of course, the map is highly transcendental. Okay, so the point here is that this is an upper triangular matrix. It's unipotent in some sense. And yeah, so the key point is that in on the Durham side, everything's kind of canonical because up to scaling these forms, there's this exact sequence split. And so everything's kind of fixed. In other words, the Durham thing is graded in some sense, it's the direct sum of the two pieces. In the Betti setting, that's completely false because there's no way to choose, there's no way to split the last arrow. There's no way to choose a path from 1 to alpha in a nice way. So what that means is that we can change the Betti basis. And as we all know, changing the Betti basis just means, it's just restating the fact that the log is a multi-valued function. So that log is not well defined. You can add some multiple of 2i pi, where n is any integer. So on the level of this matrix, that's simply saying that we've just changed the Betti basis in a certain way. And what that is precisely right multiplication by this matrix group. So the ambiguity, if you like, is this period matrix is well defined up to right multiplication by this group of matrices. So this is the monodromy group, and as is standard in sort of differential Galois theory and so on, you want something algebraic. So we take the algebraic closure of this group, and as an algebraic, the Zariski closure of this thing is the additive group. Is the group of matrices of this shape, additive group. And that's the Motivic Galois group. So let me just give one example. So what we've shown with all this, let me just take alpha equals 2. So we've shown that log of 2 is a period. We've written it as some integral of algebraic things.
What you did in this matrix, what is this star? It's not Z, it's not.
So this is, well, it's a group scheme. So it's something that can be anything in any commutative unital ring. So the Q points would be where you take all elements in Q. So Q R G A of R is the set of these where star is in R. There you go. For any commutative unital ring R. Yeah, so what do I want to say? Oh yeah, so log 2 is a period, and we've in some sense computed what the Galois action has to be, because it's going to have to respect all the monodromy properties of the function logarithm. So the idea is to, instead of trying to understand a Galois action on numbers, we want to replace this number with something more algebraic, and that is the class of the differential form dz over z, which sits in M Durham alpha, and the cycle gamma 1, and then that's it. So a better way to think about the number log 2 is instead of an integral, instead of it's just a number, it's a pair of vector spaces. They're two-dimensional vector spaces over Q. We have two vector spaces, and in each vector space we have a distinguished element. And how do we get the number log 2 from them? Well, we apply the comparison, the Durham comparison map, and pair them together, and you get back the number log 2. So it's a way to replace the number log 2 with something that's much more algebraic. And then the idea is that there should be a group that acts on all the category of such algebraic structures and preserves all possible compatibilities. So in this case, it will have to preserve the sub thing that's on the left and the quotient thing on the right. So there's no choice. The only thing it can do is change the extension data. That precisely says that log 2 is going to have to be sent to some multiple of 2i pi plus log 2. So from this we want to construct a group. And so this data is algebraic. And from that we're going to construct groups. How am I doing? Okay. So now I'm going to
But log 2 was a period in the sense of the original sense.
In the original, oh, so yeah, I didn't say, so gave the naive definition, and I'll say it in words, that the smart definition of a period is you take some diagram of, let's say, smooth schemes of finite type over Q, and you compute the relative de Rham cohomology, the relative Betti homology, and you look at all the numbers that come out in the period matrix. That's the period.
Like log 2 was a period in the original sense.
Log 2 was a period in the original sense as well, yeah.
But the two senses are equivalent? Or is it just a sort of...
Yeah, so maybe I think they're more or less equivalent. There's some small variations you see. So yeah, in this sense, the two senses I gave, they should be equivalent. Yeah.
It's clear now
so I
that
know
it's the second definition which is a good one.
the second definition is a good one. The first definition really should be discarded. It's not very functorial.
Take it as a provisional definition, the first one.
Yeah, but the idea is that you can somehow take any such situation, look at small affine charts, in the quasi-projective case, map to some open in Rn, and then everything's going to be mapped to something algebraic, and retrieve the original definition. Okay, so yeah, so to finish this idea, so it's going to be a little bit more technical. Specific periods. So I'll just quickly explain how one can get a group out of this, and then try and tie it in with the Grothendieck-Fleischmann group. So in a very general framework, one can take T a Tannakian category, so this is an abelian tensor category with some extra structures, positions, and I want to consider two fiber functors, and I'm going to call them omega Betti. They're two functors from T to vector spaces over Q, finite-dimensional vector spaces over Q. Betti and de Rham, for the sake of argument. So examples of such categories, well, you could take, very naively, you could take just something like pairs of vector spaces with a comparison isomorphism between them. That would be the sort of the first approximation to a motive. Would be the de Rham cohomology of something, the Betti cohomology of something, and some comparison isomorphism between them. That would be a very sort of cheap approximation to a motive. Of course, there are other structures on cohomology. There are hot structures, weight filtrations, hot filtrations, and so on. So a better thing to take would be a category of mixed hot structures, but better still would be to take an actual category of mixed tape motives, about which I'll say nothing. But really, this is the thing that I want to bear in mind. And then what we have is P is the isomorphisms from from de Rham. So the isomorphisms of these two fiber functors. So this is a collection of maps which, for every object M, gives some map like this, which are compatible with all possible morphisms. And what is a motivic period? So a motivic period is a function on P. So let's just start to be familiar with what we saw in Dror-Bar-Natan's talk. We had looked at the set of isomorphisms between two different objects, and it will turn out to be precisely the same thing in one particular example.
Is this some sort of regular function? Is P a co-algebraic group, and then you take... What do you mean?
Yeah, this is some kind of group scheme.
What's a function?
No, it also.
Yeah. Okay. Yeah. It's a byte also. What I mean as a function. it's a function from P to Q. The function, so so this is some kind of this is some pro-algebraic thing, and it's going to be the ring element in O of P. So it's actually it's going to be some pro scheme defined over Q. I can speak of its functions, of its Q valued functions.
Affine scheme.
Yes.
In this case.
Pro-affine scheme. Yes. So very concretely, I take an object M in the category, some class in the RAM of M. So thinking of differential forms. So gamma here I've been a bit shifty. So Betty downstairs. So typically this is going to be Betty cohomology. So I should really dualize. So that's why it's slightly different from what I did before. And what is the function? So the function on, so if I take a Q point of P, then,
excuse me,
yes.
Third one, MBM should be omega BM.
Oh, thank you very much. Oh, yes. Omega B of M dual. Yeah. And then I can, so phi M is something that maps, I hope I've done this right, from Durham to Betty, so I can map phi M moves this class into Betty, into omega B of M, and then we have an element in the dual, which then sends it to an element of Q.
Sorry, what are you defining here, P? Or because I don't understand what's meant by phi in PQ.
Phi in P of Q. Now, I'm sorry, I'm not going to explain in very great detail what this is. This is
P is indeed a scheme defined over Q and you take the Q rational.
the Q, exactly. So I've defined the function on the Q rational points. So strictly speaking, I should take any. I should view this as a functor, so I can a functor on any commutative unit or range. But you know, if you know about this, fantastic. If you don't, it's not. I just wanted to quickly, I just wanted to quickly give an idea of why we get groups out. And okay, so then we have, so acting on P, we have G de RAM. And so yeah, this part of the talk is not very introductory. I apologize. It's just to try and tie in with what we should know. So we have G de RAM, G Betty. So of course G de RAM is the automorphisms of the fiber function de RAM, and G Betty is the automorphisms of omega Betty. So we get a P is indeed a bi-tensor of these two groups, which again affine group schemes. So over Q. And so what do we get from this? So this data of this integral has become this algebraic, this sort of triple of cohomology, and then the classes in its different realizations. But now we have the action of a group, in fact two groups, on such objects. So what have we gained? We've got, say, for example, the GDR action on motivic periods. So the cost of replacing numbers with triples, these elements in some Tanakian category with two functors, whatever that means, we gain the action of some group. And so this is precisely the Galois action that I was alluding to at the beginning. So what does it do? Let's go back to our example log 2. So I can put a little m, log 2 motivic, to mean the data of precisely this data here, this algebraic version of log 2. And from the calculation we've actually done, we see that this group is going to have to preserve, it's going to act as GL2 on this 2x2 vector space, and it has to preserve the various structures, so it's going to be unipotent, and in fact it's going to be exactly this thing. Well, in fact, I failed to say something. One can also scale the basis forms dz over z. We can scale this and dz by rational numbers.
Could you explain why you've given up on GB?
GB.
Yes, you just.
Just B is better because.
No, but I mean, you only seem to be using the action of GDR.
Well, it's kind of the same because they're isomorphic. It's a torus, so we can do that.
Just a group order too.
Okay.
I agree with you that.
Got you.
I agree with you. Betty is better because when we did the example, it was the Betty classes that had the ambiguity. So we want to really think of paths, we're changing paths. The Durand forms are fixed, but I personally prefer to use Durand because it's easy to calculate with, and you can do a lot more. And it's hard to think in terms of paths. Whereas Durand is very algebraic; it's much easier to compute with. You're absolutely right. I can take Betty, and then here I can have mu 2I pi motivic, which is the motivic version of this. Which is again, it's the same matrix, but where I select this entry. By these algebraic calculations, we've computed how a putative Galois group should act on the number log 2. And in fact, we've made it rigorous because you can indeed carry out, there is such a category T, and these algebraic structures. And so this is, okay. So now in the very last part, I just want to say some very brief things explaining what on earth this has got to do with the conference topic. So of course this is an extremely general program to extend Galois theory to a whole class of transcendental numbers is a huge thing. Turns out that the Grothendieck-Teichmüller connection will be a very, very tiny part of this program. And I should specify this is the unipotent before someone asks me. This is the unipotent part of Grothendieck-Teichmüller theory. And of course, I'll only look at the genus 0 case for now. So what we had was, let's look at a very particular class of periods, multiple zeta values. So this is the algebra of multiple zeta values defined in Herbert's talk. And apart from the fact that these things keep cropping up all over the place, the reason why they're important is really because it's the first, it really is the first non-trivial example of such a Galois extension of periods. So we can do a motivic version. So we can replace these numbers with algebraic data, with vector spaces and isomorphisms, Hodge structures, and so on. And it has some group. And the question is, what is this group? So G is the motivic Galois group. And the miracle is, so this really is the miracle, that we can actually compute some partial information, but actually in practice quite a lot. We can compute some partial information about the action on the multiple zeta values. And that kind of will be the purpose, the ultimate goal of my lectures, to explain exactly how we can compute that and get the formulae. And it has sort of a very operatic sort of flavor to it. So what is G? So G is the group which preserves all possible, so I like to say all motivic, in some sense conjecturally all possible algebraic relations between MZV. So you can imagine this is a very complicated thing because it has to respect the shuffle, the double shuffle, all these identities that were mentioned in Herbert's talk. So it's a group this group of symmetries of all these equations. Now, okay, so now what we know is that this group is contained in GT1. The unipotent genus 0 Grothendieck-Teichmuller group. And the folklore conjecture, which is an amalgam of conjectures of lots of different people, is that G should in fact be isomorphic to GT. So this is why the multiple zeta values connect in some way to the Grothendieck-Teichmuller group. And so at this point I'd like to say, so if it were the case, so no one expects these groups to be different. If it were the case that they were different, and I had to put my money on one of these groups, I would put it on G, on the Motivik-Galois group. In my mind, the G is a very, very deep object because it is controlling the cohomology of all possible algebraic varieties, all schemes. GT is some explicitly defined group that relates to a specific geometric situation.
Sorry, just one question.
Yes.
Is 3 needed to define G here? It's not clear for me.
What's
the link between 3 and 4?
the link between 3 and 4?
Oh, between part C and part.
Ah! What's the link between part 3 and 4? So we have these multiple zeta values. We can play the same game and write them as cohomology of something. Actually, I'm going to say that in a minute. Write them as cohomology of something. That something are Durham vector spaces, Betti vector spaces. And from that data, one can hope to try to compute that we know that there must exist a group. We can try to compute this group and try to compute how it acts.
So G here is GD here for some...
Absolutely. So some extremely... So here we have the world of all possible periods, or even any Tannakian category with two fiber functors. Now I'm going to take something very specific, just the first examples of periods that we've found so far in
so
nature.
you will tell us who is T here in this case?
T, I'd rather not. So T in this case, okay, so T in this case is the category of mixed tape motives over which are unramified over the integers. So there exists some abelian category of mixed tape motives over any number field. You can take the category of mixed tape motives over Q and from that extract a subcategory that's totally unramified. I'm actually not going to talk about this in the talk. In the lecture, it would take us would take too long. But there is. So this is really the reason why the multiple zeta values keep appearing everywhere, because this is the category. So you take cohomology of projective spaces, a bit like we did in the examples with P1 minus forms, and you ask what are the cohomologies, relative cohomologies of algebraic varieties, which are extensions of these simple building blocks. You take the simplest possible building blocks, which is cohomology of projective space, and you ask what are the motives, cohomology groups built out of these pieces. That's the category. That's some category of that's some mixed tape motive. And then you say, okay, that's a little bit too big. That contains things like log 2, which has some problems at prime 2. Let's take the ones which are totally unramified. So this is the most simple, most natural class within that very simple class. And it turns out that the periods of these things are exactly the multiple zeta values. So that's the reason why the multiple zeta values keep appearing time and time again.
Could you spell out the way more primitively, going from GDR? So we had a GA that we computed,
Yes.
but this is supposed to tell us something about a Galois group over a Q, because what we have there is a Galois group of some numbers.
Yeah.
So what's the sort of
It's a Motivik Galois group. It's some matrix group. And so what we know, okay, so we know that the Galois, actually what I'm saying. So we know the Galois group of this, so G is isomorphic to a semi-direct product, U, so let me take Durham. So GM is the same GM we had before, the same lambda, it's just something that scales, that keeps track of the weight. Okay. And U is a pro-unipotent.
So are you sure that the semi-direct way would oppose
Oh, okay. I want to do that. So U is pro-unipotent. Pro-unipotent. And what we know from very deep results in algebraic K-theory is that it's Well, it's graded by the Lie algebra is graded by the action of GM. Its graded Lie algebra is isomorphic to the free Lie algebra. Freely on certain generators where there's exactly one sigma in degree 2n plus 1. So these are precisely the Soule classes that you
I was
know.
asking just for the
So that's the structure.
elementary link between defining GDR
Yes.
and then having the Galois group of all of the images of those periods you constructed.
Yes.
So you constructed some functions to Q,
Yes.
but then these periods are also over Q,
Yes.
and we take the whole field of them and look at its Galois group.
Yes.
What's the connection between that Galois group and the motivic Galois group?
I'm not sure I fully understand, but it's extremely hard to know. If I just do this naive approach with periods, you can define some group, but it's extremely hard to know what its structure is. So when I said here that we happen to know the structure, sometimes you've got to control all possible, you've really got to work very hard to do this. So the fact that we know this in this case is extremely deep results.
I think
I'm
what
not sure I
Justin
understand the
is
question.
asking is that you've been talking about moving around transcendental numbers, and then
You want to extend scalars to Q
yeah,
bar?
and then
Oh
you
yeah,
no, and then you say that one says, and it's true, that it's related to the Galois group of some algebraic number.
Oh yeah. Oh, so you're saying
So
it's
it
just-
sounds
it's just one of
paradoxical.
these- what are they called? These. I can't remember. Yeah, it's a disjoint extension. It's I can put Q bar in. It makes no difference.
Yeah, but it's also related to the Galois group of.
Oh, so okay.
of the
So
maximal
how's it related to
for-
Galois? Okay, so
It's also related
okay.
to the Galois
So if I take mixtape motive, there's an L-adic realization. Right. So I'm going
Yes.
way off.
No, I know there's an L-adic realization.
So okay, so the
I
L-adic
want
realization
that
gives you a
from-
category with a fiber functor to vector spaces with Gal Q bar over Q actions.
That's true.
So there you get your connection with Gal Q bar over Q.
So that you're saying that defines a map from GDR to Gal Q bar over Q?
No, well, you have to take some L-adic completion, so you get a map from Gal Q bar over Q to, if I've done it right, GDR tensor to QL. And then, but then that's what it does. It factors through the graded Lie algebra associated to Gal Q bar over Q, as defined by EHADA and so
Could you
forth.
say
So
how
you get
you
back
get a
exactly.
map from, so say you have a functor to...
Could I do that after 15 minutes over and... Sorry, this is going off and down. So yeah, so what's the connection with GT? It's that. Oh, so I was saying, yeah, that's right. That in my mind, so in Dror Barnatan's talk, he said people write papers saying A and is related to B, is related to GT, therefore it's deep. Now, I would argue that GT is deep because it's related to G, and of course, yeah, and this whole philosophy of periods goes way beyond just mixed techniques. So very quickly, what are the steps? The steps in the course. One, I won't actually follow this direct cohomological means of trying to compute groups that way because it's actually hard. It's not actually been done that way. There's a sort of a shortcut that goes via looking at the fundamental group. And so the basic protagonist is M04, which is P1 minus 3 points. And as we saw in previous talks, we can look at the fundamental group and take its unipotent completion. Again, I should iterate this whole motivic story has nothing to say about the profinite, or very little to say about the profinite story. So this was defined in Dror Barnatan's talk again. So the point is that this pi1, so we know the binionization of pi1 is something cohomological, but it turns out the whole unipotent business is the cohomology of something. That something turns out to be moduli spaces of curves of genus 0. But in any case, you can take the Betti and the Durand realizations of that thing, and what you get is some Betti fundamental group and it's going to be isomorphic to some de Rham fundamental group. Betti fundamental group turns out just to be essentially just the Q points of well, it just turns out to be exactly the Fourier completion, exactly defined in George Barnatan's talk. It has a group GB acting on it, and then on the de Rham side you get something pretty concrete, and you have a de Rham group acting on it. And if I replace so the periods that you get out of this picture is precisely the multiple zeta values. And so that's really all you need actually for the Mativik story. But this should be compatible with all possible morphisms with all other schemes and so forth. So a good thing to do is to look at M05. And this is just M04 cross M04 minus the diagonal. And then I can put a 5 here and a 5 here. And then this, the fundamental group is something related with braids. So when you take the unipotent completion, you get almost exactly what you call B, which is brilliant because B stands for Betti. And then when you take the de Rham side, you get something which you call C, which was good as well because that stands for de Rham cohomology. It's intentional, of course. And you looked at the isomorphisms from one to the other, and on the left you had a group which you called GT, I think, and on the right you had a group called GRT, which was the graded version. So why is this side graded? Well, as we saw in the de Rham cohomology, you have this it splits for Hodge theoretic reasons. So that's why you get the graded on this side. And the set of all isomorphisms was called ASOC. So, in conclusion, this period sort of setup applied to the very specific example of the fundamental group of this particular space precisely gives back this entire GT setup that we saw in the previous talks. And that's all I'd like to say. So sorry for running through.
Later, I would have a few philosophical
Philosophical remarks are good.
I mean, technically philosophical.
Well, I don't know whether my question is philosophical or not, but you have this for the Tanaka category. You can consider also for the Tanaka, there's also a group-wide version where you consider many fiber functors.
Right.
And so you could consider, for example, periods which take pairs of Hom sets.
Mm-hmm.
So it looks like a one cochain in the cohomology of a Tanaka groupoid. You see what I mean?
Off the top of my head, I don't get the. I don't know what's the.
So you make a groupoid scheme
Yes, absolutely.
out of a lot of fiber functors.
Yes.
Now you took two objects in this groupoid
Yes.
scheme,
Yes.
and you take a function on the Hom set there.
Yes, exactly.
That's your period.
Yes.
Okay, but you could also take functions.
Oh, no, I see. You want to view that stage. I see. That's interesting. Yeah, that's I've not thought about it. That's a good one.
So why are there only two fiber functors?
No.
Well, they are. There's a whole torso of them. I mean, there are.
Okay.
The point is that you want to retain.
The group has two objects.
I didn't. I forgot to say that, but there's a canonical. The point is that we want to retain the link with numbers, and there's a canonical comparison between these two fiber functors. There's the God-given isomorphism. So there's an element in the complex points of the scheme of isomorphisms. And this is very important because it exists. You know, there's a whole torso of them, but this one is given by integration. So integration defines a point on this. And this is crucial because it enables us to retain a link with numbers. So what are numbers? What are periods? Well, it's you take a Mativik period, which is a function on P, and you evaluate it. Evaluate on this complex value point, and that gives you a complex number. So that's crucial. It's really crucial to have
specific error.
Yeah, you have they're an array of God-given fiber functors. Motives. Comoji has certain comoji theories. There aren't, of course, you can twist them around by applying any element of P, but there are ones that come naturally. Durand theory, Betty theory, and that's really crucial to retain that because, and in fact, to prove all these theorems, you need to use this in a crucial way. You really have to. So the thing is that you have a very tenuous grip actually on how this group acts on things, and you use this to map to real numbers. You do some analytic computation in real numbers, which gives you some information, like a non-vanishing or vanishing of some element. You bring it back to your group scheme, and you have this constant back and forth between. So this is really crucial. Yeah.
No, I think what you should consider also elastic functors.
Yeah, well, but in principle, this gives you enough. Everything should be contained already in the Hodge size. But true, yeah. One should consider everything. One should use all the tools one has at one's disposal, and there are very few of them. So.
I would propose you to ask quick questions if possible. We are already very late.
The question is simply that the Doram isomorphism is not only algebraic, but it's also it preserves the K product in the sense that you can extend as an A infinity map.
Yes.
So I'm asking if you cannot restrict to isomorphisms which have this property to get a smaller group.
Well, the group is really massively restricted.
No, it doesn't.
Anyway, I don't think it. Yeah.
It doesn't make any change.
It's the group. So a priori when you write down the Tanaka group, you get the impression it has no structure because it's just endomorphisms on all these vector spaces. But it sees all the substructures, all the quotient structures. It sees everything, and that's enormously restrictive. And in the course, we'll see that if you just look at pi one of p1 minus 3 points, you have different choice of base points, and it gives you some. So this picture, different piles, a groupoid structure, and simply knowing that the Galois group preserves the structures here enables you to say an awful lot about it. So you get a lot of information from Octave. For example, like the tensor product is not really needed. Tensor product doesn't play such a. You don't need the tensor product to describe the action.
When you say period, do you include 2πi inverse?
Sometimes.
In your definition, you say.
Yeah, in my naive definition, I didn't. So yeah, you're absolutely right. So in motives and so on, it's very it's necessary to do tape twists, and that means you invert. So if you look at residues or isomorphism and stuff, so that means on the level of numbers that you have to invert 2i pi. So one could call it an effective period. An effective period. So P would be effective periods, if you like, ones which actually come out of cohomology of varieties, and this is with some small detail. And then one can extend.
It's like with divisors. You have positive effective divisors.
Yeah, exactly.
It's exactly the same.
Pierre, you want to make a bit too long?
3 minutes would be too long.
So, thank you again.